Hi there, method students. In this video, we're going to look at discrete random variables. We'll talk about what they are and then how we can make calculations associated with them. So, some definitions here to start with. A random variable is something that can't be predicted, but is determined by the outcome of an experiment. And these random variables can either be discrete, which is where the list of possible outcomes is countable, or continuous, which is a measured quantity such as mass, height, or time. So we're pretty used to, we've probably learned about discrete and continuous variables in statistics, and they mean the same kind of thing in probability. So discrete variables are counted, such as the number of pets in your house or something like that, or the number of pets in lots of different people's houses. And continuous variables are measured, so things like the height of a tree or the length of something or the temperature or the time or something like that. Anything that's measured is continuous, anything that's counted is discrete. So discrete variables usually take whole numbers if they're counted. They don't have to, you can certainly count some things by halves and that sort of thing, but in most cases a discrete variable will take a whole number value because it's something that's being counted. Okay. A random variable is a function that assigns a numerical value to each outcome in the sample space. And remember that sample space just means all the possible things that can happen. A random variable x is said to be discrete if it can assume only a set/countable number of distinct values. And that's kind of probably a little bit repetitive there. It's what we said up above. So let's have a look at some examples and kind of piece it together as we go. So let's suppose, and this is a pretty common one we've looked at a lot of times, that we toss a coin 3 times. Well, we know that the sample space for that experiment is, and we could get this from drawing a tree diagram, but the sample space is heads, 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 tails, and so on. And we know there's actually 8 different sort of outcomes when we toss a coin 3 times. Or 8 different combinations of outcomes, I suppose. If capital X represents the number of heads appearing uppermost, what are the possible values of X? Well, this is just saying if we toss a coin 3 times, what are the different values we can get in terms of the number of heads? Well, I guess we can either get 0 heads when we toss a coin 3 times, because we could get tails, tails, tails. We could get 1, which just means we're getting 1 head out of 3 tosses of the coin. We could get 2, or we could get 3. Right? So the different values of X that we can get in this experiment are 0, 1, 2, and 3. It's possible to get 0, 1, 2, or 3 heads when we toss a coin 3 times. Is X a discrete random variable? Well, yes it is, because clearly the values that we're obtaining, the number of heads that appear uppermost, those are values that we're counting. We're either going to be getting 1 or 0 or 2 or 3 by counting how many heads we get out of 3 tosses of the coin. Okay, so example 2, this is a bit of practice with just the whole discrete versus continuous idea. This one just says which of the following represent discrete variables. So anything where we would count to record the variable, that's going to be discrete. So number of goals scored at a football match. Yes, that's discrete because that's counted. The height of students in a maths methods class, well, no, because you measure height, you don't count it. So that would be a continuous variable. The number of girls in a family of 5 children, yep, that's discrete. The giveaway is the number of, usually means it's going to be counted. The time taken, no, that's a measurement, so that's continuous. The number of cars passing a toll booth each hour, yep, that's discrete, it's counted. The number of heads, yes, that was our example above. And the amount of time, so no, measured, that it takes to correct the cooling device and the air conditioner. As soon as it said amount of time, we knew that was going to be a continuous variable. Okay, so all the ones I've ticked there are the discrete variables because they're things that we would count to record them. Okay, discrete probability distributions. Straighten that up. Discrete probability distribution shows all possible outcomes the discrete variable can take, as well as the probability of each outcome occurring. So typically we'll see these in a table, and it looks like this sort of picture you've got here. And this table is going to show you some information about what the possible outcomes are, but also the probability of those outcomes occurring. So just in terms of notation, because you'll see some confusing looking notation in this section, typically the variable will be assigned a capital letter, which is commonly X. It doesn't have to be, but most commonly you'll see capital X. Lowercase x represents the possible outcomes, right? So not the overall variable, but the possible outcomes that variable can sort of have. And the probability that capital X equals lowercase x is the probability that the variable takes the value of a particular outcome. So this might be easier to kind of explain when we look at this table, which shows a probability distribution for the discrete random variable x, where x represents the number rolled on a fair 6-sided die. So we know that the possible values of x, which is this lowercase x here, are 1, 2, 3, 4, 5, and 6. This row here that says probability that x equals little x, excuse my dog barking, is showing us the probability that the variable takes each of these individual values. So in other words, the probability that we get a 1 is 1/6. The probability that we roll a 2 is 1/6. The probability that we roll a 3 is 1/6, and so on. So that's kind of how you can break down this table, and it's probably a nice simple example because it's one that we've seen lots of times, or thought about lots of times, is rolling a fair 6-sided die. And what you'll notice about this table, and with any discrete probability distribution, is that the following 2 conditions have to be satisfied. So each individual probability has to be between 0 and 1, And that can include 0 and 1. So we know we can have a probability of 0 or a probability of 1, but it can't be outside those values, okay? And in our rolling a die example, we can see they're all greater than 0 and less than 1, so that's no problem there. The second key feature of a probability distribution is that the sum of all the probabilities equals 1. Okay, and that's what this notation is saying here. That symbol there means the sum. So the sum of the probabilities is equal to 1. That makes sense, right? Because this table is showing all possible outcomes. So one of those outcomes has got to happen, right? So when we add the probabilities together, the chances of at least one of those things, or like one out of all the possible things happening, has to equal 1, because something has to happen, right? One of these results has to happen. And so that will be true of any probability distribution, those two key conditions. All right, let's get into a couple more examples. So this next one is actually coming back to it's a bit repetitive, I know, the 3 coin tosses. And this is saying let X represent the number of tails obtained in 3 coin tosses. Construct a table that displays the values the discrete random variable can assume and the corresponding probabilities. Well, we kind of know from the example 1 that the possible values we can get would be, we get 0 tails, we could get 1 tail, we could get 2, or we could get 3, right? That's the possible number of tails that we can get. And even though we probably know this one really well, if we super quickly just redraw our tree diagram for 3 tosses of the coin, what we can also do is find the probability of each possible outcome for the number of tails. So for example, if X is going to equal 0, if we're going to get 0 tails out of 3 tosses of the coin, well, that would just be if we get heads, then heads, then heads, right? That's the only one outcome that results in no tails out of 3 tosses of the coin. And remember that the probability of each of these sort of results individually is a half. So the probability of heads, heads, heads equals a half times a half times a half, which is 1/8. Okay, so we can put that in there, that the probability that we get 0 tails out of 3 tosses of the coin is 1/8. As we make our way through, well, we know that each of these 8 sort of outcomes is going to have a probability of 1/8. So if we're looking at our next possible outcome, which is that X equals 1, in other words, we get 1 tail out of 3 tosses of the coin, well, that can happen in a few different ways. That can happen if we get, I'm just going to write them down over here, heads, heads, tails, heads, tails, heads, or tails, heads, heads, right? So there's 3 different ways that we can get that result. And we know, I'm not going to keep writing out the half times a half times a half thing, but we know that each of these has a probability of 1/8. So altogether, that would give us a probability of 3/8. So there are three equally likely outcomes out of 8 that would give us 1 tail from 3 tosses of the coin. We also know that for 2 tails, well, so this is for, I guess, 1 tail. This working's not super clear. It's probably not the standard way of working out. We're just sort of looking at all the different outcomes here. So for 2 tails, well, we could get tails, tails, heads. We could get tails, heads, tails, or we could get heads, tails, tails. And so again, there's 3 outcomes out of 8. We've done these probabilities before in previous examples, so hopefully this particular context is pretty familiar, but it's a good way to demonstrate how we set up these probability distribution tables. And of course, if we're going to get X equals 3, well, that means we're going to get 3 tails out of 3. And the only way that can happen is if we get tails, 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 and we know that that probability is a half times a half times a half, which is 1/8. And what we should notice when we fill this table in is that we've got all our probabilities are between 0 and 1 inclusive, so they can equal 0 or equal 1, but together, each of them individually has to be between 0 and 1. And if we add them together, if we add these probabilities together, they should add up to 1. And 1/8 plus 3/8 plus 3/8 plus 1/8, that equals 8/8, which is 1. So we know that satisfied the conditions of a probability distribution. All right, let's have a look at a couple more, and we'll sort of see, I guess, ways that questions can sort of throw different things at you with these discrete probability distributions. So example 4, we have to actually show that the distribution for the random variable X shown below is a discrete probability distribution. So we really just have to show that the 2 conditions are satisfied here. The first one, remember, is that, let's write like this, that each individual probability is greater than or equal to 0. And less than or equal to 1. And we can kind of see that by inspection. The probabilities are 0.2, 0.5, 0.2, and 0.1. So that condition is satisfied for all PR X equals X. The second condition is that the sum of the probabilities needs to equal 1. And we can show that just by adding them together. 0.2 plus 0.5 plus 0.2 plus 0.1. Well, we get 0.2 plus 0.5 is 0.7, then plus 0.2 is 0.9, then plus 0.1 we get to 1, so equals 1. And so we've shown that the 2 conditions are satisfied, and that is a discrete probability distribution. All right, example 5, and this is a pretty common type of question. So find the value of k for the discrete probability distribution shown below. So here what we're really looking at is the probabilities, and you can see that k is a probability, but it's missing. But if we know that the sum of the probabilities has to equal 1, well then that just means that 0.2 plus k plus 0.2 plus 0.3 plus 0.1, all those probabilities added together has to equal 1. So let's add up all these other ones that we do know. We get 0.2, 0.4, 0.7, 0.8, so k plus 0.8 equals 1. And so subtracting 0.8 from both sides gives us k equals 0.2. Okay, back to a sort of worded problem here with a context. So Francine drives past 2 traffic lights on her way to work. At each traffic light, there is a 60% chance that she'll need to stop. Let y, so not always x, this is y, let y represent the number of traffic lights at which Francine must stop on a trip to work. And we've got to start by calculating a probability distribution using this table. So let's think about it. If there's 2 traffic lights that she can stop at that she's driving along, well, the possible number of lights she'd have to stop at, well, she might get lucky. She might get 2 green lights in a row, so she doesn't have to stop at all. So y could equal 0. She might have to stop at one set of traffic lights, but not the other one, so y could equal 1. Or she might have to stop at both sets of traffic lights, which means y could equal 2. So those are our possible values for y. And if we sort of think of it as a tree diagram where she either have to, let's just say she has to stop or not stop, stop or not stop. Well, what we can do is find the probability of each of these things happening. So the probability that she has to stop and then stop, again, well, it's a 60% chance that she needs to stop, so 0.6. So 0.6 times 0.6 equals 0.36. So the probability that she has to stop twice would be 0.36. The probability that she has to stop once, well, that can happen 2 ways. That can be she stops at the first light and not at the second. And that would equal, excuse me, pencils losing its sharpness here. So 0.6 times, I didn't put all these probabilities on the tree, but 0.6 and 0.4 would obviously be the probability that she doesn't have to stop. So I should fill those out. So 0.6 times 0.4, that equals 0.24. So that's our probability that she stops at the first one, but not at the second one. And then other way around, if she has to stop at the first one and not at the second one, well, that's just going to be 0.4 times 0.6, which of course will also equal 0.24. And so altogether, the probability that she has to stop at one set of lights only is going to be 0.24 plus 0.24. Okay, so the probability that she has to stop at one set of lights is 0.48. And the probability that she stops at neither, so she doesn't have to stop at the first set of lights or the second set of lights, well, that's just 0.4 times 0.4. And 4 fours are 16 with 2 decimal places, that's 0.16. All right, and then we can do a quick check, at least in our heads, that when we add these values up, they're going to add to 1, because the probability should all sum to 1. So 0.16 and 0.36 gives 0.52, 0.52 plus 0.48, yep, they add up to 1. Okay, now we've got the table set up. Calculate or determine the probability that y is greater than 1. Okay, so that just means that she has to stop more than once. Well, because this is a discrete variable, if she has to stop more than once, then that just means she's stopping twice or more. And in this case, that just means it's the probability that y equals 2, which is 0.36, okay, because she can't stop more than twice. This one here, the probability that y is greater than or equal to 1, well, that just means the probability that she has to stop once or more. And again, in this example, that's probability that she has to stop once, or probability that she has to stop twice, and she obviously can't stop any more times than that, so they're the 2 things that we've actually got to add together. So 0.48 plus 0.36 gives us 0.84. All right, and calculate the probability that Francine has to stop twice on her next trip to work, given that she has to stop at least once. Now that phrase, given that, doesn't always have to be there, but it's commonly there in conditional probability questions. And as soon as we know it's a conditional probability question, my number 1 tip is to actually write the formula. So we're finding probability that she has to stop twice, so probability that y equals 2. Oops, shouldn't have closed that bracket yet. Given that, so probability that y equals 2, given that she has to stop at least once, so given that y is greater than or equal to 1. And once we write the conditional sort of statement like that, the right-hand side kind of comes together just using the formula. So remember, it's the probability of both. It's the probability that y equals 2 and that y is greater than or equal to 1, divided by the probability of the condition, the thing that we know has happened, the probability that y is greater than or equal to 1. So if we think about this top statement, if y is going to be equal to 2 and greater than or equal to 1, well, that just really means that y is equal to 2. So it's the probability, on top it's the probability that y equals 2, and on the bottom it's the probability that y is greater than or equal to 1. And now we just find those two values. So probability that y equals 2, we can go back to the table, that was 0.36. And the probability that y is greater than or equal to 1, we actually found that in the previous part of the example, so it's 0.84. And we shouldn't have decimals within fractions, so we can make that 36 over 84. I'm running out of room here, aren't I? 36 over 84, what's it going to simplify down to? I think 12 will go into both of those, won't it? So, excuse this funny way of writing it, but if we divide the top and bottom by 12, we're going to get 3/7. And there we go.